And the session of this morning will be focused on the Bethe Salpeter equation and how to describe excitons in extended systems. And the first speaker is Fulvio PALEARI, who will guide you through the derivation of the Bethe Salpeter. He will not use the standard one, but he will use a derivation based on real-time propagation. Please, Fulvio.
Thank you, Davide. I hope everybody can hear me. So, as Davide introduced, I'm Fulvio PALEARI. I work as a postdoc in Modena. Today is the neutral excitations day at the Yambo school, which means, for our purposes, bound electron-hole pairs, which are called excitons. As you can see here in this simple picture, here we have a band structure, a hole, and an electron. We've seen yesterday, for example, with the GW method, we can compute quasi-particle corrections, which typically enlarge the band gap. But actually, when we study neutral excitation, for example, light absorption by the electronic structure of the material, sometimes in semiconductor, the light absorption happens at an energy that is lower than the band gap. And this is because of the electron-hole interaction between the excited electron and the hole that remains in the conduction band. So basically this picture. In particular, we can imagine that when light impinges on a material, a macroscopic polarization, rapidly oscillating in time, is generated, and the absorption spectrum is just the Fourier transform of this polarization. So the frequencies that are encoded in this polarization end up as peaks in the absorption spectrum. This is also the path that we will take for giving a sketch for the derivation of the Bethe Salpeter equation, which describes electron interactions. Just to, okay, sorry, I should point it here probably. Well, okay. Okay, so. No, but it's connected to my laptop, so I think. Okay. Ah, no, now it's working, okay. So this is basically the outline. I will give you a brief introduction why we need to go beyond the independent particles picture to describe a response function like the one for optical absorption. Then we will sketch this derivation starting from the equation of motion of the response function in real time. We arrive at the Bethe Salpeter equation, and at the end I will give you some examples of possible application of the BSE beyond optical absorption spectra, okay? So why do we need this? Well, okay, we can imagine we know more or less about DFT. If we know the band structure of the system, we can also compute the absorption spectrum. So it's just a matter of knowing the wave functions, of knowing the energies of the bands, and then we can compute this spectrum. And this is given basically by the Fermi golden rule that you can find in every book. We have the transition matrix element describing the coupling of the Kohn-Sham wave function with light, and then the possible transitions because of energy conservation happen at the transition energy between valence and conduction. However, if we apply this formula, let's say, to a material like lithium fluoride, so let's say we do DFT, we also do GW correction, why not? We obtain basically the red curve for the absorption spectrum, while the experiment shows this very sharp peak, which even lies below this red curve. No? So actually there is something deeply wrong in this formula. And the corrected formula, let's say, that allows us to describe this case as this shape. As you can see, it is a linear combination of the transition matrix elements across all possible electron-hole transitions, weighted by these weights. We will obviously explain these later on. And the energy of the transition is not anymore the valence to conduction transition energy, but this new exciton energy. So these red quantities that I am outlining here come out of the solution of the Bethe Salpeter equation. And you see that if we apply this new expression, then in this case of lithium fluoride, we get a pretty good description of the optical absorption spectrum. There are even more, well, lithium fluoride is pretty striking, but the best application of the BSE probably is in layered and 2D systems. I look, for example, here at monolayer hexagonal boron nitride. Again, I do DFT plus GW, compute the absorption. The absorption starts at the quasi-particle band gap, and it's like this potato-shaped curve. But then I try to solve the Bethe Salpeter equation and check the difference in the independent particles and the excitonic absorption spectra. You see, it's like completely different. all the oscillator strength is sucked at lower energies in really well-defined peaks that are, okay, now you can see, basically almost like discrete states. And so this is a very striking case. The difference between the quasi-particle band gap and the main peak, for example, is the binding energy of this exciton state, which is almost 2 electron volts. So this happens in such striking fashion into the system because, of course, as was explained by Alberto yesterday, the screening of the interaction between electron and hole is pretty weak into these systems, and therefore the binding energies are quite high. Okay, so now that we understood the need to go beyond the independent particles picture, we can try to think about how to do this. There are several ways to get the Bethe Salpeter equation. For example, here there are kind of 3. One uses the Edin's equations, which you have already seen for GW yesterday. This is a totally doable strategy, but since we have already seen it yesterday, we will not do it today again. Then there is like the Schwinger approach, which employs functional derivatives with respect to the external potentials, and we will see a version of this approach, but basically starting from the equation of motion of the response function. So this is an approach that can be easily extended to treat out of equilibrium systems, while approaches that are based on a frequency space cannot be extended out of equilibrium. So this can be interesting also for applications beyond optical absorption. Okay, so as always, we start from the electronic Hamiltonian, so kinetic term, electron-nucleus interaction, and then the electronic interaction. Here you have the Hartree term, which depends on the ground state charge density. And then here I just put the Fock term. So this is just Hartree-Fock, okay? And I do this because doing this with the DFT exchange correlation functionals makes the equation a bit more clunky, but it's totally doable. In these slides is like this just for simplicity, let's say. And then, of course, from this electronic Hamiltonian of non-interacting single particle energies, we can get the eigenvalues and the block functions. And from the block functions, we can also get the charge density at equilibrium. This we already more or less saw this the other days. But the quantity that we are interested in is the response of the system when an external field, an external time-dependent field, is added to this Hamiltonian. And then the situation becomes like this. We have our equilibrium Hamiltonian, we have the external field, but then we also need to account for a change in the electron-electron interaction, because now the Hamiltonian gets an induced, the density gets an induced component, which is time-dependent because it is induced by a time-dependent field, and so the functions of the density must also change a little bit. And therefore we have to add these pieces here, which are just the difference between the equilibrium electron-electron interaction and the time-dependent ones. Okay, now of course we can get the density matrix of the system, this time time-dependent, not anymore necessarily at equilibrium. You can get it, for example, as a time-equal limit of the single particle Green's function. And then we can finally get to the quantity that we are really interested in this presentation and today. The response function, which is here the variation of the density with respect to the external field. So we would like to find an equation of motion for this response function, which includes electron-hole interactions. Of course, the response functions, just as the charge density, can be expressed from the position basis, can be transformed into the single particle basis, which would be the Consham basis if you did the DFT calculation. And then actually we will mostly work in this basis, where N1, N2, N3, and 4 are single particle indices. Okay. So now, well, the equation of motion for the density matrix is pretty simple, no? It's just the Heisenberg equation of motion. So it's the commutator of our operator of choice, this time the density, with the full Hamiltonian of the system. But then we can think about a way to transform this into an equation for the response function. We just take the functional derivative of both sides with respect to the external field by doing this. So this side becomes an equation of motion for the response function. But then we have to kind of compute the functional derivative of these commutators. And let's say the most difficult part of this is computing the functional derivative with respect of the electron-electron interaction parts of the Hamiltonian. For example, let's consider the time-dependent Hartree term. We can actually immediately rewrite it just as a functional identity, making the functional derivative with respect to the external field appear here. We did nothing, basically, this is just an identity. But now we can apply the chain rule here to transform here this in a derivative with respect to the density. So we apply the chain rule, but now this additional term is just the definition of the response function. So we basically transform this variation into some kernel, let's say, which is then a tensor product with the quantity that we want to find, the response function. We can do the same things also for the other part of the electron-electron interaction, in this case the Fock part. And finally, the sum of the two will have this shape, basically a kind of two-particle kernel. It's two particles since it depends on 4 single particle indices. Now we will see better what this means later. And then this is much easier to calculate, as we will see in a moment. In fact, for example, this is the Hartree term. So basically we have a density loop and the Coulomb interaction here. We can just replace here the single particle basis expression for the density. So this goes out of the integral, and we just get basically the density matrix product with the matrix element of the Coulomb interaction. Keep in mind that because of momentum conservation, this term will be only evaluated at 0 momentum, or the momentum of the incoming field at the end of the calculation. We can do, okay, so in the end we arrive at this expression, it's the same as before, and then the functional derivative is pretty easy, in this form. This is the time-dependent Hartree. Take the derivative, we just get the Coulomb matrix element, basically. We can do the same for the exchange part of the self-energy. This is just the Fock term. So here I wrote rho to maintain consistency. This is, we can also call it the Green's function at equal times of the system. And this is still the Coulomb interaction. Now, this, here we have a problem in our treatment, because if we just keep going, so we do exactly as we did for the Hartree term, so we rewrite these in the single particle basis. Now we have a problem because this bare Coulomb interaction is bare, it's not screened, and therefore it will give wrong excitons. So we have to actually replace this with a screened version of the interaction, so to avoid the overbinding of the excitons, and also to be consistent with what we learned yesterday, the GW case. In fact, we just replaced V with the statically screened electronic interaction, and the static screening is in the RPA approximation. So this is exactly the GW approach. Now, this is transformed. It's not anymore pure exchange. It's not anymore the Fock term, but it's the screened exchange. So the approximation for the electronic interaction that is commonly used to compute excitons is the so-called Hartree-X, so Hartree screened exchange approximation. Now we can continue after overcoming this obstacle. Now we can write the screened exchange part also in this way. Notice the different sign with respect to the Hartree part. We can compute again the functional derivative that we need to get to the equation of motion, neglecting the functional derivative of the W itself. Now W in principle depends implicitly on rho because of the screening. But this is an higher order term, we don't consider it, and then we get this simple expression. So to bring everything together, now for our equation of motion of the response function, we get basically the commutator with the non-interacting Hamiltonian, okay. Then the commutator with the external field, okay. And then we get this part that we just computed, which contains this W minus 2V, which is the electron hole kernel. Now we can actually in practice, what does this mean? For example, the first term is pretty easy, it's just this commutator. We can apply H naught on the left and on the right, and we just get the differences of the single particle energies, in this case. In the case of the field, so remember that we are in linear response, so we are at first order in this field. Therefore, for the rho, we can use the ground state value, the equilibrium density, and then we apply this also in this fashion to the left and to the right of the states, and we get the equilibrium occupation of our system. Instead of here is the difference of the energies, here is the difference of the occupations. And then the last complicated term actually is treated in exactly the same way, so it's basically the same steps. After we do this, we finally have a simpler expression for the response function, the equation of motion for the response function. Now consider that since we now are explicit at equilibrium, so we have used the equilibrium quantities in the evaluation of the commutator, now actually it turns out that the chi is just dependent on the differences of the two times. And then here we have finally this k, which is what we computed before. I just put it together in a single variable, w minus 2v. Now the difference in sign plays an important role because the w acts as an attractive interaction. So this is the binding term. This is responsible for the electron bound state appearing below the quasi-particle band gap of the system. And instead, this Hartree repulsive contribution is normally much lower in value, in magnitude than this. So in the semiconductor of interest to us. So in general, when we have this kernel, we can find bound excitons. Okay, so now let's switch to a different basis, which is the transition basis. As we can see, we are now explicitly considering transition from the valence band, so N1 is now a valence state, to the conduction band, so N2 is a conduction state. So we can just label this double index with a single index, the transition index. And in this way, we kind of simplify a little bit this equation because now it depends on 2 indices instead of on 4 indices. Okay, perfect. Now, finally, we are almost at the end, right? We can just do the Fourier transform of this, since in the end it depends just on the difference of the times. We can Fourier transform this. And then if you, okay, try to do, if we put k to 0, then it means we are putting to 0 the electron interaction, and then we need to go back to the independent particles case. And indeed, if you do it, you end up just with chi equals to this quantity. So it's written in a kind of compact form, but you can recognize it's the same chi naught, independent particles response function that we discussed yesterday. But now we have an additional term, this kernel. And therefore, finally, we can write it as probably as it is most known, the Bethe Salpeter equation as Dyson-like equation. And this is kind of a diagrammatic representation. This is the response function. The box represents the fact that the electron and holes are interacting in a complicated way through this box. We have first a non-interacting case, the bubble diagram, and then we have the interacting part with the kernel. Okay, and this is also the point of arrival of the other derivation approach that I outlined at the beginning, the one based on Edin's equation. In the end, you get to this expression. Very good. And of course, the kernel is composed of these two terms that we just described. Perfect. Now we have to solve it. So normally, when you have a Dyson equation, you try to invert it. And this is what we are also doing here. We try to factorize all the term with chi on one side. And then if we just keep omega alone, we see that what is left has kind of the form of an effective Hamiltonian for two particle states. So if we just call these H, let's say, then we can kind of invert it and place this on the other side of the equation. Okay, so this we called H, and then we invert it. And we get something like this, formally written. So you see, this actually starts looking more and more like a propagator, no? Like a Green's function, because in a Green's function in reciprocal space typically is the inverse of omega minus its relative Hamiltonian. And in fact, this is kind of the point here, because now this Hamiltonian contains all the information that we were after at the beginning, for example, to describe excitonic corrections to optical absorption spectra. The eigenvalues of this Hamiltonian, that is what is technically diagonalized inside Yambo, give the exciton energies. And instead, the eigenvectors give the exciton coefficients that we were discussing before. So now we can write this in this new lambda basis, which is the exciton basis, in which it is diagonal, obviously, since we diagonalized the two-particle Hamiltonian. And therefore, finally, if we want to go back to the transition basis, we just have to perform a change of basis. So basically, we arrived at the end. And we basically see that we have reduced, let's say, a problem that started from a complicated equation of motion for the response function to an external field of the system to basically just a linear algebra problem, just diagonalizing this effective Hamiltonian, which contains an off-diagonal part that encodes electron interactions in this Hartree screened exchange approximation. So these are all, of course, not time-dependent, not frequency-dependent, all static interactions. Okay, and now this effective Hamiltonian that we need can just be computed with the techniques that we already know. So for the energies here, the single particle or quasi-particle energies, we can use DFT plus GW or various things. The wave function, we will use typically the DFT wave functions, the Kohn-Sham wave functions, and then we just have to compute the RPA screening to compute the W, the statically screened interaction in the screened exchange approximation. And that's it, basically. This is what kind of Yambo does. In the next lecture, Davide will enter into much more details about this and about also other technicalities. So now I'm kind of skipping over many things. But I thought, at least in this way, I can give you kind of a initial understanding of what we mean when we say, okay, we derive the Bethe Salpeter equation, we solve the two-particle Hamiltonian, we get the Exciton information. Now I come to the last part in which I want just to give some examples of how we could use the BSE. We could use an excitonic picture beyond or in addition to simple optical absorption, well, not so simple, but optical absorption measurements. I think our guest speaker today will probably give a much better overview, but still I will give you some examples. So the first natural extension of what I said is, okay, so far you were implicitly considering the case of optical absorption, therefore of macroscopic fields in which the momentum of the incoming field is like much smaller than the extension of the Brillouin zone of the system. But what happens if we instead we want to consider excitons with a finite momentum? Well, then we would need to diagonalize the Excitonic Hamiltonian for each finite momentum, a different Hamiltonian for each momentum. This is kind of similar, if you know phonons, to what is done for the dynamical matrix in the phonon case. And then we have a Q-dependent exciton basis. And this describes, you see, a non-diagonal transition, indirect transitions, for example, from a valence state at K minus Q to a conduction state at CK. So it's basically indirect transitions. And when you solve the BSE at finite momentum, you can, for example, compute exciton dispersion relations, kind of what you do when you compute phonon dispersions. This is, for example, an example done with Yambo. We are solving the BSE at various Qs, various transfer momenta in the Brillouin zone of monolayer MOS2, and basically we get the dispersion of the various excitons. It's a very badly made plot, but just to give you an impression of what can be done. A better physical insight we can actually get from this paper. So maybe you will talk a bit more about it, but I just want to mention some interesting things that can happen when you study exciton dispersion. For example, this is monolayer MOS2. And this is the exciton, this is like the brightest, well, the first bright exciton of MOS2, the A exciton. It turns out this is a doubly degenerate exciton. And when you go away from Q equals 0, it splits. And it has an interesting dispersion. Basically, one component goes parabolically. And this is determined by the screen interaction that kind of gives this parabolic dispersion. But the other one is dominated by the macroscopic component of the Hartree interaction, which gives this linear behavior, at least close to Q equals 0. And another interesting case is this one of solid pentasine. As you can see, this bright exciton has kind of different energies at Q equals 0, depending on the direction in which you take the Q equals 0 limit. And like in particular, if your direction of Q is parallel to the polarization of the incoming field, so let's say it's a longitudinal direction, you have a higher energy than the case in which well, the opposite case when the direction is orthogonal, and so you have kind of a transverse direction. And this is the so-called longitudinal transverse splitting of the exciton states. Maybe you know it from the phonons. Again, the analogy with the phonons is very nice. Maybe you know the LOTO splitting, longitudinal optical and transverse optical mode splitting. This is a kind of a similar effect. Well, obviously this ties into something that is very important at the moment for research, which is basically ultra-fast, out-of-equilibrium experiments. For example, pump and probe experiments. In this experimental setup, what do? You first create excitation in the system with a pump pulse. Then there is an excitation and relaxation dynamics. And then at a certain time, you probe the system with a second pulse and check the state of the system. And in systems where excitonic effects are very important, you kind of see complicated signatures in these pump and probe spectra. For example, these are time-dependent ARPEs. It means it's a kind of ARPEs that can probe also empty state, also conduction states, while regular ARPEs normally is confined to valence levels. But here, we don't see kind of a parabolic conduction band or anything. We see this blob. And the authors of this experimental paper, they say, okay, this is actually below the quasi-particle band gap. This is a kind of an exciton blob. And actually, if we wait a bit of time, we start seeing some signal here. And this could be because there is some kind of transfer of exciton from here to here. For example, some kind of complicated scattering process between exciton and phonons that could kind of move and change the momentum during the relaxation process of these excitonic states. Instead, to the right, we have another very interesting, although very complicated type of experiment. This is called a multidimensional optical spectroscopy. And for example, it is very useful to measure the broadening of the exciton peaks. In a general experimental sample, you have many imperfections over the spatial distribution of the sample. So it's not a perfect crystal, you have defects, you have like distortions and whatever. And this causes the various energy level to be a bit misaligned, for example, in absorption experiments, but also in luminescence experiment. And this adds a lot of noise to the broadening, to the width of the peak. But with this technique, you can actually remove all this noise and get to the true, or so-called homogeneous, line width of the system, which is the one that we compute when you do first principle calculations. Here you see the main diagonal is the line width of an exciton peak, including these inhomogeneities. And instead, the cross diagonal is the homogeneous line width. So it's pure, perfect crystal line width, more or less. Of course, these are very difficult experiment. And you see, this is like basically the cross section in the homogeneous direction. And people found that the line width of the exciton peaks can be reduced by 1 order of magnitude between inhomogeneous and homogeneous. So this is quite important experimentally. And where's the theory in all this? Well, these are very difficult experiments to reproduce theoretically in a very convincing way, let's say. There's a lot of discussion about the important role that excitons certainly have in this kind of experiments, but how to model this is pretty difficult. Here we can see some examples on the time-dependent ARPES case. On the left, you see this is just a model, so it's not first principles simulations. And it gets what we kind of expect from experiment. No? So this is the valence band, and then this kind of dashed parabola is the conduction band, but we don't have this. We have these exciton blobs below the conduction band. And on the right, you see instead a calculation done with Yambo by Davide, actually, of kind of the same thing. This red parabola is the conduction band of lithium fluoride. And then this energy, the distance between the bottom of the parabola and this blob, is the exciton binding energy. And at the exciton binding energy, we see, again, this kind of signal, which is a bit deformed, with actually replicas of the valence bands. So this is a kind of another complicated out of equilibrium process. We can attempt to model it using the Bethe Salpeter equation. Another important topic is Exciton-phonon coupling. This is also a difficult concept to get around. But for example, it can be used, I will give you 2 examples. One example is to reproduce phonon-assisted optical spectra. So optical spectra that are determined by indirect band gaps, mostly. No? So in this case, we have bulk boron nitride, and the photoluminescent signal, actually this is cathodoluminescent signal, is determined by the emission, the recombination basically of some excitons at finite momentum, and they can only recombine emitting light via the help of a phonon, of several phonon modes. And these are basically the satellites, the phonon replicas that assist in this recombination. Because it turns out that, for example, the strength of this exciton-phonon interaction is kind of proportional to the second order derivative of our response function, including the BSC, with respect to atomic displacements along the various phonon modes. Another way to compute this exciton-phonon interaction is to basically do a merge of first principle types of calculations, density functional perturbation theory, which is used to compute the phonons, and many-body BSC, which is used to compute the exciton. And then by doing this merging, you can also get the exciton-phonon coupling strength. And in this paper, you see here, this is not a band structure. This is an exciton dispersion, also of bulk hexagonal boron nitride. And the colors represent basically what the authors calculate as the relaxation times of the excitons. So basically how much time, typical time the exciton takes once it is excited by a pump pulse to relax and go to, go to lower and lower energies. So, okay, these more or less were some examples from the literature. Of course, this is a difficult problem, as is the problem in general of non-equilibrium quantum mechanics in these condensed matter systems. There are many things that can be done here, also a kind of a fundamental level. This, I will give you just an example of something that we are trying with Yambo. When you compute the phonons, this you will see this better tomorrow, you already include inside the phonon calculation the contribution of the electronic Hartree interaction to get reasonable phonon frequencies. But this contribution is also, as we have seen, inside the exciton. So what we are trying to do now, so this is a double counting, right? What we are trying to do now is to remove this double counting. So, for example, to see what happens if we compute the exciton-phonon coupling strength, like removing the Hartree interaction for the excitons. And as you can see from these plots of the matrix elements, these were done also with Yambo. The orange is the one with the double counting, and the blue is the one without double counting. You see, qualitatively, we have, of course, the same structure, the same symmetries, the same phonon modes coupled with the excitons. This is monolayer molybdenum disulfide. But we can have also pretty different intensities. So, as you can see, this is not the final answer, but it's just to say this is a very complicated problem. There are many things to be studied, many interesting approaches, both theoretically, purely theoretically, but also from the experimental side and from the explanation of the experimental signals. There is also much to do. So welcome to this field if you are interested. And yeah, with this, I just conclude with a summary. What we have seen, that the independent particle picture is failing in the case of many semiconductors, especially layered materials, two-dimensional semiconductors, to reproduce important spectral features, because we are not including in the standard treatment the electron-hole interaction. This we can get it in a very general framework in which we try to model the dynamics of the excited electron system out of equilibrium. And for example, from the equation of motion of the response function, then we can kind of recast it in a kind of effective two-particle Hamiltonian form. This is the standard Bethe Salpeter approach. And this yields the excitonic picture that, as we saw, can be used to kind of improve our understanding on a variety of spectroscopic phenomena. With this, I thank you for your attention. And before the end, let me give you some references. So basically, if you're just interested in learning about the derivation that I sketched in my slide, without maybe too much context, I will just suggest these two papers, the bottom two. So these are papers in which this kind of derivation that I have shown is done very well, okay, with all the steps and everything. If you are more interested in also learning the context of how one can do many-body physics in a time-dependent framework, of course, there is the book of Karanoff and Baim. And then there is the book that we already mentioned many times, the book of Gianluca Stefanucci and Robert van Leuven. Honestly, I don't know which one is more difficult. Like you say Karanoff and Baim, but actually, yeah, okay. Try the first 5 chapters of the Stefanucci, then you tell me how it is. And okay, with this, I really thank you for your attention.
So thank Fulvio for this very nice talk. I recall you, the first part was really focused on the Bethe Salpeter and what we can do with the Yambo code, compute excitons and absorption. And then there was a second part which was more motivational to say once you have the exciton, you can do much more. There is a lot of physics you can explore. And now the session is open for questions. I also remember that there will be a prize for those who are in presence. We call it a prize for the best attitude. And doing questions is a part of a good attitude in the participation of the school. So we welcome many questions. Alberto.
So first of all, thank you for your nice talk. And I hope this question is not out of topic, but if you start from a GW band structure, you can also compute the finite lifetimes of the bands. So is it possible to consider these lifetimes within the Bethe Salpeter equation?
Okay, so this is actually a much deeper question that than I hoped for, but okay, try to reply.
Just to say, if you just plug in if you just plug in the complex part of the bands in the diagonal part.
No, this would be totally wrong.
Okay.
Okay, because the BSC rests on the fact that you are using inside single particle, well-defined single particle states. So you do not use the full spectral function that you get with GW. You just use the spectral peak uncorrected. You just take the quasi-particle energy and that's it. Otherwise, it becomes all inconsistent. Then consider this: if you put some kind of imaginary part of the, let's say, electronic states inside your Bethe Salpeter equation, which will describe the, broadening, relaxation, and so on, then the two-particle Hamiltonian is not anymore pseudo-Hermitian, does not anymore give real eigenvalues. And then you have to ask yourself, like, isn't it possible that I'm including something at the independent particle level that could be maybe canceled if I include also dynamical interactions in the kernel? This is actually the case. So you cannot include like higher order treatments just in the single particle case. You kind of have to find a way to also describe in a consistent way a dynamical part of electron interaction. I don't know if this is clear or not, but more or less this is okay.
Thank you very much.
So, yep.
Thank you, Julio. That was really interesting. A question about the interactions that you include when you describe Exciton-phonons in two different ways. One is the Bernardi-Trangali way that you showed, right? Exciton-phonons from the kind of Hedin's perspective, or from coupling excitons that you solve with phonons, like here, and you get lifetimes. And the other is by real-time GW, or real-time propagation, where you also include the interactions with phonons. So can you comment about the interactions you can include or not include in the two cases? And I admit I will talk about it a little bit later as well, okay. But I'm interested mainly about the real-time propagation part.
So I think in both cases, what it boils down to is that you add the dynamical part of the kernel, which depends on the first order on the phonon propagation. So it's a kind of so basically, you add, for example, the interaction of the conduction band of the electron with the phonon, of the valence with the phonon, and then the cross interaction between the two. It's called interference terms. So it's a kind of first order correction in the phonons, where the phonons are dynamical. But then this correction is not, if this makes sense, resummed in a Dyson-like way. It's just kept at first order. And this, I think, is common to all kind of approaches, right? This one, the same equivalent one that was there at Pierluigi Cudazzo, and also kind of a real-time approach. However, if you start your derivation, because you can start your derivation, and this is what was done here and also by Cudazzo, at the Bethe Salpeter level. Like I have kind of the excitonic propagator, I have the excitonic Hamiltonian. Now I kind of perturb it with an additional term with the phonons. And then you get this. What you could do instead is go to the beginning of my slides and put electron-phonon interaction inside the main general electronic Hamiltonian. In this case, you would be away from the standard Hartree approximation. You will have to include a kind of a vertex function in the phonon. So you will have basically the GW interaction, more or less, is the Hartree approximation, plus a kind of fun Migdal type self-energy, so G times the phonon propagator, times the vertex. And this vertex will have to include all electronic interactions. So also kind of an excitonic, at the excitonic level within this vertex. And if you do this, it comes out very similar to this, but with an important difference that basically is this one, that the excitons, since the vertex that you will include in that fun type self-energy is the vertex without the Hartree interaction, so it's the so-called irreducible vertex, then you get excitons like this, without the Hartree inside, with only W inside. So you get slightly different, and depending on the system Hamiltonian, and then this is basically the difference, for example, for MOS2, in some unphysical Exciton-phonon matrix elements at Q equals 0 that I computed. Unphysical because these states are too far away to interact with a single phonon energy, not because the calculation is wrong. So you can see there can be kind of an effect. So there is a difference, and we are now finishing our work with Andrea Marini, in which we explain all of these very well with all the cases. And yeah, it remains to be seen, you know, what this entails for the future. Then maybe probably in your talk you'll say, no, this is all wrong, I already did it. But okay.
So, yeah, thank you for this very advanced discussion. I mean, here we are discussing things which are really at the frontiers of the present research. I would like to have much more basic questions for the students A short question here. As far as I know, the Yambo code can also use the Bethe Salpeter equation to calculate magnon spectra.
To calculate, sorry?
Magnon spectra from magnons, spin waves.
Okay, yes.
Yeah. Could you say a few words on how the Bethe Salpeter equation can be extended to the magnetic interactions?
Yeah, so no, I'm not doing that because the expert is Davide. So I think he will probably talk about it a bit in his lecture, but maybe if you want.
There will be a slide on that.
Okay. Okay.
So maybe we can check if there are questions from the audience of online.
Hello.
Yeah. Yes, please.
Hello. Yeah, a very nice presentation. And actually, I'm curious about that ARPS plot that you have shown for excitons. And what is the material actually you have chosen? ARPS exciton plot.
So if I understand correctly, you're asking me about which materials I've shown in these examples?
Yeah, ARPS plot.
Ah, the ARPS. Ah, okay, yeah. So
yeah, this one.
This
yes.
one should be tungsten, transition metal dichalcogenide, tungsten something. I think tungsten diselenide, right?
WS2, okay.
Right.
And I just want to ask, like, here you have shown you're saying that this is the exciton, like when light is interacting, so there must be many. So is it a single one, or how are you like explaining this exciton?
So you still, your question is still about this figure, no? The left one?
Yeah. Is it a monolayer?
Yeah, no, okay, thanks. Yeah, no, it's a bulk. So since this is a layered system, in transition metal dichalcogenides, you still have strongly bound excitons also for bulk systems. So basically here they had some independent way to determine the position of the quasi-particle bandgap, okay? Then they did this time-dependent ARPS, and they saw basically this signal, this very weird-looking signal below what should be in their determination the quasi-particle bandgap, and therefore they assign this to an electron all-bound state. They say, okay, this is an exciton, and this is kind of they have done this in this experiment.
Okay, then I've seen a nice question from Enesio Marino from the online audience. Can unmute yourself? So otherwise I do the question myself. So the question is about the screening. He says, so we are doing all this complex BSC theory, but then we still use the RPA screening. So why do we do that?
Well, I mean, let's say it's the simplest approximation and the most consistent with the many-body treatments in general that are implemented in codes. Also, you may think of this as a kind of improvement with respect to the RPA screening. So the RPA screening is already a small improvement with respect to just the independent particles case. And then we kind of add even more physics inside it, and from RPA it becomes BSE. But then you need the step before to go to the step after that, if that makes sense.
Okay, and then another question from Rajet Dut, if I spell it correctly, if you can unmute yourself as well. Rajet Dut.
Thank you, sir. Very nice presentation. Actually, because we are talking about the excitonic states, so I'm wondering whether these excitonic states can be used or to study the metallic optical spectra, or it can help us to understand the metallic system as well.
Okay, so in general, it's kind of a bad idea to try to apply Bethe Salpeter to metals, exactly because of the screening problem. So metals are very heavily screened, they do not have a gap, and dynamical effects in this screening are extremely important, while here the way we are treating electron-hole interaction is just at the static level. So most likely, if you try to do that, you will get wrong results. Also, even, in addition to the dynamical screening, the dynamical effect problems, there are also some details inside the Excitonic Hamiltonian that I didn't discuss about that need to be adjusted. Basically, I'm referring to what is known as the Tam-Dankov approximation. This is a standard approximation that simplifies the Excitonic Hamiltonian, but doesn't hold for metals. Maybe you will understand more about this in the talk of Davide's talk, in which he will explain these blocks of this Hamiltonian much better.
Yeah, a much more basic answer is that in metals the screening is so strong that usually electron and holes do not bind, so you don't have excitons.
Yeah,
and then
okay.
of course there are,
I agree, but you could have kind of modifications in the absorption.
Sorry, if I can add on that, what you said is totally correct, but still there are in literature calculation on metals. There is a famous paper in the Stephen Louis group showing the existence of bound excitons in metallic carbon nanotubes. So there is work on that, and there are cases when you can find interesting results.
I would say in semi-metals, not in metals.
Semi-metals, you are correct.
Any more questions from the audience here? Yep.
I think Enesio Marinho Jr. asks to read the questions.
Yes,
I
think we already did that. So I wonder if everything you said is also valid for core excitons. Is the physics still the same?
I think generally yes, but maybe Davide, you can answer to this.
So yeah, I would say that in general for core excitons, the electron-hole binding energy is even more important because the hole is pretty much localized, so it tends to interact a lot. And there are at least two groups who worked on using Bethe Salpeter to describe core excitons, and you can do that and it works pretty nicely. So we have time for one last question before the break.
May I please ask?
Yeah, sure.
Okay, so can we do bi-exciton calculation using Yambo? There was also one question in chat box. Same.
So I think Yambo right now is not able to do compute ions or bi-excitons and charge excitations like that.
Okay, thank you.
Okay, that was quick. And also I see a raised hand by Neha Kapila Sharma, if you want to to do your question.
Yeah, I asked it earlier. Thank you so much.
Yeah, sure, yes.
Okay,
just
sorry.
the end remained, but.
Okay, sorry.
You wanted to say something about bi-excitons?
No.
With the convolution of the density matrix beyond linear response. So in Yambo, we can calculate nonlinear properties. You are calculating 3-point Green's functions and 4-point response functions. You cannot disentangle bi-excitons from single exciton trions, but there you have free body interactions in an uncontrolled way. But they are there.
This is a calculation that the user can do?
What?
Is this a type of simulation that the user can do, like running Yambo?
Yes.
So let's say the standard implementation of the BSC is in frequency space. You directly compute the response function, and that is just for excitons. In the real-time propagation, you can go beyond the linear regime, and you can have much more effects somehow. But in the implementation that we have at present in Yambo, we linearize the kernel dependency with respect to the interaction. So I think you will not capture bi-excitons and this kind of effects. But maybe we have to discuss. So let's say that at least the real-time propagation formulation could be prone to include more easily these kind of effects. Okay, so time for the coffee break, I think. So we are perfectly on time, and we have half an hour of coffee break. We resume in half an hour.